Bharatwaj sir, shall I start?
Sir, you can start. I'm ready.
Okay, thank you. A warm welcome to one and all present for being a part of this international webinar for 2 days. I take immense pleasure in welcoming you all. The webinar is a topic is based on envision towards particle science and biodiesel production. Today's topic is a research pathway in particulate processing of materials. The session is going to handle by Dr. A. Rajesh Kannan is associated with Mechanical Engineering, School of Engineering and Physics, FSTE, USP, SUA, Fiji. Since 2008, he has been a part of this university. He has joined as a lecturer and raised to the level of associate professor in the years of term. His primary research areas related to materials, manufacturing, and industrial engineering. In particular, metal forming, metal additive, CNC machining, and operations management are the area where the research work is focused. Nearly 75 articles were published in this field in the referred journals and conferences. He also secured an Australian innovation patent to tool designing. He set up powder metallurgy research lab for research purpose and developed metallurgy and manufacturing lab for bachelor's professional for mechanical engineering program. He earned Bachelor of Engineering, Master of Engineering, and research, that is PhD in mechanical engineering from India, and he put up an academic and research experience of 7 years in India itself before he moved to USP Fiji. Let us not waste his time. We hear from horse mouth. Respected sir, the forum is yours to enlighten us.
Oh, thank you, Mr. Balaji. Good morning. My name is Kannan. I'm originally from India, but like I said, I moved to Fiji from 2008. All right, so the topic that I had given today to you is a research pathway in particulate processing of materials. Let me start from here. Why this research pathway? Fundamentally, research in students' perspective is important to acquire a depth of knowledge in a chosen field or interested field. The depth of knowledge is essential in order to be skillful in the field. The skill is essential in order to find a placement in the job market. So, apart from doing our bachelor's degree, I'm not telling you to go for master's or PhD, whatsoever it is, but getting a deep knowledge in a particular field, unless we do research, unless we do meditate in that, it is difficult to acquire. So therefore, the research is the suitable term in that way. The second thing is about the pathway. The pathway is all about the approach. Usually it should be systematic approach. The reason for going systematic approach on a particular topic is always like one thing. We have to make meaning out of our activities that we do it in order to demonstrate our knowledge, right? So finally, like end of the day, if we get results or if we get output out of our research activity, we have to make sense out of it. So it is therefore essential to make a systematic approach, which is nothing but pathway. If it happened to be the research pathway in your own interested field, and that would be really nice, because you don't feel that you're working hard, like otherwise, like you really work hard, which doesn't give you a fruitful results to you, because you don't have attachment with that field. So it's always recommended to choose your own field and then keep moving on. So this is all about today's topic, a pathway in a particular field, that's PPM, where I was working in that field for the past more than 1 decade. Okay, at the end of the day, when we complete this presentation, what we learn out of it is really important. I just put that one first presentation slide. This is the learning outcome. I had put here as a means of asking question, is this field, I mean to say ppm, possess a potential research problem? And this is really a good question. Is this field possess a potential? Does it really has the potential to do any research, or is it like we have attained the saturation state and nothing more to do in that field? So the answer to that first question is the answer to the second question. As you see here, does the research problem be complex enough to meet publication criteria or to fill the research gap in the contemporary literature? I had put little, like in an official term, I should rather be stating here simply, if you make any research problem, the methodology or the solution that you are getting out of it shouldn't be like in a obvious, like in a very trivial manner. You should have made some engineering approach to get the solution out of it. Only then it makes sense that we have done some engineering into that particular problem. So such a way the research problem you have to be formulating, that should be complex enough. In detail about it, I'll discuss when we enter into that topic. The next is like, end of the day, whatever you do, that's immaterial unless and otherwise it feeds you. Our bread and butter is really important. So that's I stated, will this field be recognized for job opportunity? That's really important. And the last one is one obvious question always arises, like this field, is it like sustainable for long term or never ending process or something like that? So answer to these questions you'll be able to find at the end of the presentation. So this is our learning outcome. So before I begin the topic, you may be interesting to know, like, where is exactly this Fiji and so-called the University of the South Pacific is located. So to just entertain you in that mode, let me talk about the location and then I enter into a topic. Here it is. I'm not sure you really heard, but when I had come to 2008, I was really unknowing about this country, Fiji. But surprisingly, during the time before 1947 and so, India is much aware of Fiji. But in later part of time, I don't think so. But anyway, here it is. So this large area, this part of it is called Pacific Ocean, that connects from let's say eastern end is Japan to Australia, New Zealand, like this border, and the western end is like United States, I mean North America and South America. From in the screen, I would rather say this, the east is states like America, and then this side is Australia and New Zealand. So this vast portion is Pacific Ocean. This Pacific Ocean, if you carefully see, there is a line in between here. This is equator line that bisects the Pacific Ocean into north as well as south. And there is a vertical line, as you see here. This is international date line. So what does that mean? Exactly at this location, if you assume there is a 6 p.m. today is Monday, at this point 6 p.m. today Monday, and this location, it is 6 p.m. yesterday, that is Sunday. So which means that it's an imaginary line basically. The day starts from here and it moves like this. All right, so in the South Pacific Ocean, there are plenty of islands which we are not aware, because our knowledge would be limited to go up to Australia and New Zealand. Maybe thousands or more than that islands, number of islands, and some of them or many of them are really it doesn't, people are not even living there. And if you look at it, this is the location which we call it as Fiji. Anyway, I'll show you that in here. This is Fiji. Again, it has plenty of islands, but then important island is these two. This one is Vanvalevu and this one is Vitilevu. Within this Vitilevu, you can see this is Suva, which is the capital place of Fiji. And that's this is Suva. in which University of the South Pacific is located here. And now about the University of the South Pacific, it's this. Only there are 2 regional universities in the world, and University of South Pacific is one. The other one is in the Caribbean islands. If I'm right, that should be University of something like West Indies or so. The meaning for regional university is like nearly 12 countries. These are the countries, 12 different countries together running this university. In each country, we have campus, but in Fiji, we have a main campus. All these countries you can see around here, like this is Fiji, and this Tonga, Samoa, Tuvalu, Kiribati, Nauru, Solomon Island, and so on, Marshall Island, together running this university. This is about introduction about Fiji as well as the USP. I hope we stop here and then we go back to our topic. Thank you. Let's move here. All right, set ppm. Let's start from the scratch. Particulate processing of materials. We go one by one. The particulate means it representing very small particles, particularly you can say solid particles. You can say in the form of powders. That's about particulate. The processing, you must well aware of it. The processing means sequence of operations or the step-by-step operations. See, unlike the particular operation is done, the successive operations may not be performed. So that's it means. It's a sequence of operations. The last one is about materials. Typically, for now, for the sake of our understanding, materials are meant to say metals or ceramics and so on. But in this particular case, it is like small particulate metals or small particulate ceramics and so on. Basically, you can say metal powders or ceramic powders and so on. So what we do here, we use this small solid particles. We do some kind of processing on it. Through this process, we are producing a part that is used in industrial applications. Right. So how and why all those things are our topic of interest. Now, before we get into the deeper into it, we will see what are the materials classification. In your textbook, mostly in BE, first year or second year, we will be studying about the materials classifications. In a textbook context, usually the fundamental classification is this: the metals and alloys, ceramics, glasses, polymers, semiconductors, composite materials, and so on. Nothing wrong. This is really fundamental and it is important. But as you move on, like little advanced to it, this fundamental classification is no longer going to help you. You know why? Because it's all depends on the functional or the application based. Those classifications are here, like aerospace, biomedical, and so on. Why it is, for example, if you take aerospace applications, it's not that one material is going to satisfy the entire purpose of the aerospace. For example, metals alone is not going to satisfy. It's a combination of many, like metals are there, ceramics are there, polymers are there, semiconductors are there, like composite materials are there, like almost everything comes into play, an important role in that particular function. So that's the reason, like a little advancement to that is like a functional classification, aerospace, biomedical, electronics, materials, and so on. In each field has got a vast like ocean of research is been going on successfully. And now this is like application based. The next one is little advanced, is like a technology based, like for example, a nanotechnology or functional graded materials technology and so on. Now, looking at this, the one thing that we will understand, like the development of materials, the research on developing the materials is a never-ending process. As long as the world exists, as long as we human being exist, and this is going to continue. And it's a kind of one of the evergreen field, I would say. The next is processing. Okay. All right. So this is like processing. I mean to say that materials processing technology. Immediately the question arises, like how do we put all the materials, or how do we manufacture the materials? Keep one thing in very important in our mind. Whenever you develop a new material, okay, or whenever you develop, you make existing material, whatever it is the case, the two important thing is really important. You know what? The first thing is the material that you develop should be manufacturable. Okay, you should be able to manufacture to the design that you have made it already. So that's first thing, manufacturability. The second thing is, even if you manufacture through a set of process, that material should satisfy the functional properties. What does that mean, functional properties? Take any example, like in an automobile, if you take camshaft, or if you take piston, if you take crankshaft, it does some function, like it does some operations. So while it does some operations, it undergoes some kind of you know disturbance, or any kind of external disturbance and so on, like mechanical strength or thermal strength or whatsoever it is. So in order to satisfy, it has to satisfy that, which is called functional properties. So these two categories very important whenever we develop the material. All right, so keeping this as a base, now let me explain what is the fundamental process through which that we develop the material, or we make the part. One of it is, traditionally we call it as ingot metallurgy process. In other words, a typical casting or foundry process. What do we do? Any material that you choose, we heat that material to a molten state, and we pour it into a um, in a cavity which is made out of mold, and then we allow it to solidify, and through which we get the part out, and we do some of the operations and to take it to a particular application. So this is a traditional method called ingot metallurgy process. It has its own advantage as well as disadvantage. I'll discuss about it in detail later. The other successful process, like competitive process, you say, which is called like solid state processing. You see this here, we take the material into the liquid state and then we produce as a solid. But in particulate processing materials, we use the initial materials in the solid state itself, and then we produce as a part, which is called powder metallurgy. Okay, we'll see one by one. First, if we make any, or if we develop any material, it is important to establish its characteristics or characterization. Let us see that. What is that we have to concentrate? There are two things. Suppose you make a material, like I already said, one is like it's a manufacturable. The second thing is it should satisfy the functional properties. This is exactly here. If you assume that you made a material and you have to test that to either mechanical, I said some of the examples here, but then your material you developed for a particular purpose, maybe mechanical purpose or optical purpose, electrical purpose. So directly you have to subject to this particular property test, and then you reveal it to the public or to the industry. On the other hand, this is really important. This is like straightforward. But here, suppose if you put some materials together in order to develop some new material, it's very important that the added material complementing each other, or it is like distorting each other in the matrix. You know what I'm saying? The parent material is the matrix, and then some alloying materials that you put. Maybe it is an alloy or composites, whatsoever you call it. Like. But when you put what are the material, it should complement, or it should give some kind of properties that we are really interested in. Let me give one good example so you would appreciate that. Like in our basic course, we must have studied about several bondings, and one of the example is like I guess covalent bonding or ionic bonding, in which that sodium chloride together forms a sodium chloride. You see that sodium alone as a material is a highly reactive material. I'm sorry, highly poisonous material, whereas chlorine is highly reactive material. But when you put both NaCl together, it gives a altogether different property. You know what I'm saying? As a separate material, it possesses different property, or it establishes different property, but put together it gives a different property. NaCl is nothing but table salt, which we use it for our day-to-day cooking foods or for our consumption. But if you consume Na alone or chlorine alone, for sure we are dead. All right, so this is important, like when you put together how it contributes or how it settles together. So this property is really important. How we can reveal those properties using some of the technique called scanning electron microscope, tunneling electron microscope, SEM, TEM, X-ray diffraction. So many techniques are there, which is really important to establish its basic characterization. All right, so this is all about the characteristics of the synthesis material. So what I'm trying to say here is, if you process the material, the fundamentally you have to make sure that whether the developed material really possess those properties or not, which all depends on its structure. Let me give you one flow chart. I hope you understand. The property of a material, remember, the property of a material depends on the structure of the material. Now, when I talk about structure, you can keep in your back of your mind, it could be I'm referring to microstructure, or it could be even nanostructure, or it could be even molecular structure, or it could be even atomic structure. In other words, you put it simple. The atomic structure decides the molecule structure property. The molecule structure decides the microstructure property. The microstructure decides the bulk material property. You know what I'm saying? So the property of the material decides by the structure. Now, the structure of the material decides by the process, the how you processed. Now, the basic characterization that I was explaining to you is the revealing the structure of the material. That's really important. That's the study of the structure is all about the basic characterization. I'm not going to discuss much about that, but look at this synthesis. Predominantly, we go by a fundamental approach or traditional approach that's called casting process. I had explained already what is casting process. In other words, we call that as a solid solution. You know, this solid solution. You need this fundamental in order to understand the particulate processing of materials. I'll tell you a very simple way. You know, solution is equal to solvent and solute. What does it mean? Solvent is a parent material. Solute is the second phase material. I put it in this other way. Water and salt. Water is a solvent and salt is the solute. You put together, this is called solution. Usually our brain thinks solution means it is in liquid form. You know, I hope most of you agree, because this is how I take my students have agreed to that. So solution means we are bringing it to the liquid state. So the parent material and then the alloying material all are in molten state, right? So in the molten state, liquid state, all this material homogeneously dissolved with one another, like homogeneously mixed with one another. But when you solidify it, depending on the nature of individual material, either it is completely soluble even in the solid state, or it is partly soluble or completely insoluble in the solid state. If it is completely insoluble or partly insoluble, that means your objective of making an alloy is impossible. You cannot make it at all. You must have studied that in your basic course, something called this diagram. This diagram represents binary isomorphous phase diagram. You know what does that mean? Binary means two material, parent material and solute material. So how these two material completely soluble in the liquid state, this here completely soluble in the liquid state and completely soluble in the solid state. So this is called binary phase diagram. In between is liquid plus solid, and here it is. This one is called partly insoluble or completely insoluble. So we called it as eutectic reaction. This is liquid and this is liquidous curve, and this is lead and tin. This side is temperature in degrees Celsius, and this side is tin in 0%, 20, 40, 60, 80, and 100%. Meaning thereby, tin here 100%, and here it is 0%. On the other hand, PB is 100%, and accordingly it reduces. So at any given given point, it should be 100%. All right. So this is nothing but the phase diagram. I hope most of you would know. Since I'm not able to see your face, I do not know whether you would read or not. That's why I'm explaining x and y axis including. Right. So what does this mean? At this particular location, the liquid in this state, both Pb and Sn is completely soluble, like homogeneous. But at this location, Pb separately solidifies and tin separately solidifies. So if that is the case, you cannot add Pb Sn together and make it as an alloy. So this is one of the biggest disadvantage of your casting process. All right. So this is what I was explaining about. This is one of the greatest disadvantage of casting process. Therefore, you need some alternative process. One of the best competitive alternative is ppm. One of the best competitive and alternative processing is ppr, particulate processing materials, which is our topic of study today. So you need this basic understanding. Now what I have given here is almost all the time, like exactly if I say right from the age like bronze age, iron age, and so on, like if you keep on come up to the mid of 20th century, exactly what I'm saying is the World War number 2. That's the peak of developing so much materials. You must be knowing, maybe some of your friends or your teachers must have shared with you. That's the peak of the time industrial revolutions happened and many development has been happened there. In fact, you would wonder that the steels is like a massive amount of steels were developed during that time. uh, you would be knowing that most of the steels in the European side, they numbered as en01 or en2, en3, en4 to designate the steel. You know what that en itself means emergency number. So it's sarcastically told by our research colleagues, like that time they do not even have a time to name the particular steel, so they gave it as emergency number en1, en2, and en3. So what I'm trying to say is all those period of time, like up to 20th century, if the material development means mostly we go up to the micro level of research investigation, but after some time the research investigation is like we attain to the saturation state and we have to go to the little deeper, and that's nano level investigation. So right now, or like for the past 10 years or so, the nano level investigation is like vast. So if at all you want to develop any material, it is recommended to move towards nano rather than staying in the micro level. All right. Substitutional interstitial is like something little deeper, which is not necessary, but I had conveyed what is exactly the casting process and how it is having demerit and how we are going to overcome through ppm. We'll see now ppm. Right. So now we are entering into the particulate processing of materials. Right. Now ppm has got some distinct qualities. Before that, you need to know what exactly ppm, but I'll take that part here, powder metallurgy and etc. Here it has unique advantage. I'll give you a little outline. Like I already said, the solid particles or the powder particles as it is we are taking, and then we are assume that we are compacting to a required shape and size, and then we are baking or sintering it, so we got the what you call part. So this is what all about particulate processing materials. You assume in this way. So now you appreciate what I'm going to talk about, the distinct qualities. All right. So what I'm trying to say is like compaction, you got a powder and you have compacted into a required shape and size, and then you heat it. Now you got the part. As simple. So the distinct qualities of ppm is number one, net shape or near net shape processing. Again, I'm not sure whether by reading this, whether you are understood or not the meaning for net shape and near net shape, but I give you an idea of it. What does it mean? The starting material, like the input material, as it is 100% you utilized to produce the part, then you call it as net shape. So it means 100% material is utilized, which is also called as green materials processing. There is no wastage. Near net shape means like almost 95 or 97% of the initial material is utilized to make a part, is called near net shape processing. So this is one of the distinct quality of ppm. If I say it, that is which means that I'm lying. You know why? The powder metallurgy comes under metal forming process. So not only powder metallurgy, even the forging process, the conventional forging process or extrusion process, for that matter, any metal, what do you call, what I'm saying is the metal forming process. No, any metal forming process can fall under near net shape or net shape processing, right? But the second point is really unique. It can happen only with ppm. What is that? The parts can be made with a specified level of porosity, examples filters, oil impregnated bearings, and any gears and so on. What does that mean? If you want to make a part, I want to make a part with some specific level of porosity, say for example 10% porosity or 15% porosity and so on. There is no process is existing to produce the part with the known amount of porosities. Now you wonder that why we need that porosities. Like when there is a porosity, what we do in industrial applications, those porosities are utilized to inject the lubricant material, and by the time of it is working, it subject to a mechanical as well as a thermal exposure, like thermal atmosphere. These sucked lubricant comes out by the time, and so those lubricant will act as a lubrication purpose. So that's one of the unique property. We can make it through ppm. And the last one is, this is exactly satisfying to the demerit of your casting process. Like I said, if two materials that doesn't make a homogeneity in the solid state, you cannot produce it through that route. But here, since it's a solid state processing, you can put any material together and you make it as a part. That's here. Any alloy combination is possible. Cermets means ceramics and metallurgy. It cannot go together at all, but still it is possible through ppm process. MMC representing metal matrix composite, polymer matrix composites, and so on. So these are all like unique qualities of ppm. It doesn't mean that it is like a super duper technology, like you can always trust this. It has its own challenges. We will see later after we seeing the power metallurgy process. All right, friends, here it is. Powder metallurgy, I already said it's the fundamental process is here. Primary operations. Okay, I'll come back this later. The compaction process and the sintering process. Let us see by step-by-step process. The first, we assume that we are taking an elemental powders, all right, elemental powders. And this is like just a weighing machine. We measure the known amount of material, and then we are mixing this. What is the purpose of mixing? If you want to make an alloy, it is important that these materials, elemental powders, should be homogeneously mixed, meaning thereby any sample if you take, for example, if you want to produce Fe 0.8% carbon, remember Fe 0.8% carbon. So any sample that you take, it should consist that exactly 99.2% iron and 0.8% carbon. So to get that homogenization, we are doing this mixing process. And once you make sure that you mixed, then you're bringing that to a compaction process. This is where you have to already made a die set assembly. You should have designed it. So I have given an example here. This is die set assembly. One example, you can take it like here, we are going to produce a cylindrical compact. Assume that cylindrical compact. So this is your die, and this is your the bottom insert, and this is your punch. So you pour your metal powders here, and then you do a compaction process, and through the compaction process you are producing the compact out. So in other words, this is the part that which you wanted to produce, that we have produced. So any shape and size that you wanted to produce, it is important that you have to make the die. All right. So now this die is kept here, and then the required pressure is applied. When you apply it and then you eject it, that you get this part. Because it's a cylindrical die, obviously you'll get a cylindrical part, which initial height and initial diameter, and its cross section looks like this. All right. So now after compaction, remember, after compaction, in other words, what exactly compaction means? These solid particles are forcefully joined together with high pressure. So that means each particles with the neighbor particles, a cold welding might have happened, but then still metallurgical bond is not happening. Like only a forceful the attachment is given, but the metallurgical bond, in other words, releasing the mechanical stress, nothing is there. So for that matter, we are doing a sintering process. Here it is. So in sintering, we are providing the metallurgical bond as well as we are easing the mechanical stress that we developed in the compaction process. Now, after that, we produce the part, and this is one of the example that in our research laboratory, we made the part, and out of the part, we have made some tensile specimen to undergo the functional property examination. All right, friends. So this is the fundamental operations. Now, two things is necessity to understand. One is the primary operations of powder metallurgy, other one is secondary operations of the powder metallurgy. And the primary operations, two important things. One is compaction, other one is sintering. Now in the compaction, what is really important? In order to produce the part of required density, it is important to know how much pressure to be applied. Like I was explaining the previous slide, you bring the powder and the compaction die and you have to apply the pressure, but we do not know how much pressure to be applied. So the compaction process, we have to conduct the compressibility study. To know how much pressure to be applied in order to produce the part. That's exactly this curve is all about. You see, for various density, for this you assume that the iron ideal density is 7.86, that the theoretical density. So depending on the compaction pressure, the density increases. All right. So if I want to produce like 6 gram per centimeter cube, then you have to apply this particular pressure. So this study we have to make it so that for that particular alloy or for that particular combinations, you know that how much pressure to be applied. Now the next thing is, here it is, sintering, which I said like metallurgical bond that we are producing in the part. So in sintering, two important things are important. You know what? The time and temperature. Time and temperature. The temperature is here. Usually, my friends, the temperature is given 0.7 to 0.9 times of the parent material. What does that mean? If you want to produce a steel of Fe with 1% silicon or 0.8% carbon and 1% manganese and so on, there are plenty materials, alloy materials here added. Forget about all the added material. The parent material is Fe, whose temperature, the melting point is, let us say 1450 degrees Celsius. From the 1450 degrees Celsius, you choose 0.7 to 0.9 times of that particular temperature to do the sintering process. Now, when I say 0.7 to 0.9, there is an important technical concept is that which I will explain it here. So the temperature can be from 0.7 to 0.9 times. Let us say here 850 degrees Celsius I have taken and then 1150 degrees Celsius I have taken, two different. And then the timing, let me take like 15 minutes to maximum, let's say 120 or 150 minutes. Here it is. How this time and temperature influences the percentage elongation or tensile strength or density. Let us say the mechanical properties and then the physical properties, how the sintering time and sintering temperature is influencing. For that matter, let us take, for example, sintering time. As you see, when the time is increased, sintering time is increased, obviously the percentage elongation is also increasing. As you see, there is an increasing trend. Same thing with the tensile strength too, it is increasing, but the increase is just marginal. It's not like phenomenon. Am I right? The increase at any given temperature, maybe 850 or 1150, the percentage elongation is increasing, but only marginal. Now here it is, as an engineer, we have to make a right decision. What is the optimum time that can be chosen to do the sintering process? For example, 30 minutes, 850 degrees Celsius, you can produce the part. Again, 150 minutes with this particular 850 degrees Celsius, you can produce the part, right? So when you're able to produce at 30 minutes itself, why would you go up to 150 minutes to unnecessarily waste the energy to produce the part? See, energy wastage is, on the other hand, it implicates onto the ecological disaster or ecological damage as well. So it's important. Similarly, on the other hand, the temperature, As you see, when you increase the temperature, there is a phenomenon increase in the percentage elongation as well as tensile strength. So it is important for our research, being a researcher, we have to conduct like several sintering time and sintering temperature to choose the optimum time and optimum temperature to give it to the industry people to move on. Right, so this is all about primary operations. The next is secondary operations. Here I wanted to tell you one thing. In a real time, means the primary operations itself is enough to produce the full part. Unless and otherwise something in specific you need, then you need to go for secondary operations. Otherwise, your entire job is over from the primary operations itself. Now, why would you go for secondary operations? Something like here, to increase density or to improve further accuracy or to accomplish some other additional shaping up, so on, then you go for it. For example, repressing, pressing sintered part in a closed die to increase the density or improve the properties, or sizing, coining, or machining. Because in powder metallurgy, you cannot provide threads or side holes, which you have to make it in a separate means. So this is what I was telling about. Primary operations will be sufficient to produce a finished part in majority cases. However, under some specific requirement, secondary operations are necessary. Yet the PM is not as simple that it exists no complications. We'll see the complications. Now, why would we go to challenges? I had already explained you about the topic is research pathway. Okay. And I had also asked the questions, does it possess enough complexity in formulating the research problem? That's to answer to that here. Whatever we have seen before, these are all the basics, as well as when you develop the material, what are the important things that you have to keep in your mind in order to establish is the basic characteristics and other things we have seen. Now we are seeing the PM or PPM's challenges. Here it is. Every challenge is an opportunity to frame a research problem. Keep this in our mind. Every challenge is to be seen it as an opportunity to frame a research problem. While framing research problem, it is important to note that it should constitute a complex engineering methodology to find a solution and not that of obvious approach. Well, I'll tell you one thing here. I'm not sure, like, would you be really aware of in the engineering learning process, how we are building the complexity in the student's mind. For example, I'll tell you, the first year students would be learning up to the knowledge level, like first year students would be learning up to the knowledge level, but the final year students would be learning up to the evaluation level, which is really higher complexity. It increases proportionately really higher. So your research problem should possess that complexity, like evaluation level. One example I tell you, it's given here. Suppose if you want to produce a part with high strength, okay, a part with high strength for a particular application, any applications. One obvious solution is you can increase the strength by increasing its bulkiness. What does that mean, bulkiness? Technical term bulkiness means I'm increasing the volume as well as the weight of the material. It's obvious when you increase the volume and the weight of particular material, obviously you can increase the strength of it. You note the word obviously. So that is not complex engineering. But on the other hand, you need to increase the strength of the part without increasing the bulkiness or the weight, or on contrary, you have to reduce the weight but increase the strength. Now the engineering complexity is arising. So this is what I meant, like the research problem should be complex enough. We'll see one by one now. This means challenge number one. What I meant here is there are plenty challenges are there, or the plenty opportunities are there to do the research, but these are all something like unique with the basic of what we have studied so far. Number one, right? You see this? Components are the parts produced through primary operations always possess certain amount of porosities. What does that mean? You can never or impossible to achieve 100% density. Through primary operations of ppm, it is impossible to produce 100% density. On the other hand, it means there are some amount of porosities are always existing. Now if you take it to a structural applications or mechanical applications, for example, these porosities act as a stress concentration point. Okay, the stress concentration point. As a result of the stress concentration, the material exhibits the premature failure. It fails so soon. This technical part, I hope you know that. So then how we are going to address? Obviously, there's a question arises. This is exactly a research problem for your chosen material combinations. The next is, besides, higher the density, better the properties. So therefore, from here we get to know you need to produce with high density or 100% density in order to get the better properties. But what is more important is merely achieving 100% density does not satisfy the property requirement. The mode or the way in which that you are achieving the higher density makes the immense sense. For example, I'll give you an example how to achieve 100% density. One way of doing is impregnation technique. Okay, impregnation technique. The other one is, impregnation means what? If there is a porosity, through by injecting it, injecting foreign materials or some materials, alloying materials, through which we are making 100% density. Or infiltration technique. Infiltration means like you heat the material with the porosity, and then you dip it into another molten material. So this molten material entrapped inside the porosity, through which we are attaining the 100% density. Similarly, powder forging, through forging technique, through extrusion, through rolling, or some other process there. Now you can, through a logical sense, you can easily say infiltration technique compared to the powder forging technique, which one would you feel that you get the high mechanical properties? Obviously powder forging, and not that of infiltration. So therefore, the mode by which you are making is also important to establish. Right here I have just shown one example how the density is influencing the mechanical properties. Here I have mentioned relative density rho by rho naught. I have to explain this so that you will understand this particular graph. See, rho naught means it is a theoretical density. If you take iron density, if you Google it, it says 7.876. In an ideal case, iron should consist 7.8776, meaning that by, if you take 1 meter cube of or centimeter cube of volume, right, it should possess this much mass. Then, certain mass. So that mass divided by volume is nothing but the density. That's a theoretical density, 7.876. Now this rho is the one in the numerator. Through primary operations like powder metallurgy, which is, I'm talking about the compaction process and sintering process. Through compaction and sintering, you are making a part and you measure the density, which would be around 7 or 7.2 or 7.4, whatsoever it is. Now that 7 divided by the ideal density is 7.876, which you get relative density. I hope you understand now. This is relative density. Now as you improve the relative density, you can see how strength and Young's modulus and the Poisson's ratio is improving. So qualitatively, my friends, higher the density, better the mechanical properties. So our ultimate objective is to eliminate the porosity or improve the density. So this is one of the research problem. This is not only for a particular material. Any material that you develop through powder metallurgy process, it is important to establish the densification characteristics, because that decides the mechanical properties. Keep this in your mind. This is one of it. Next, challenge number 2. Here it is. Complex geometries are not easy to produce through PM. Complex geometries are not easy to produce PM. Little focus, I'll explain you what does it mean. See, while I was explaining about primary operations, I had given you an example of showing a die set assembly where you can produce a cylindrical part. Okay, it's a very simple. Now you think about automobile parts that you wanted to produce. There are thousands of parts are there, and none of the parts are like as simple as like a cylinder. There are several complex geometries are there. If you want to produce such an industrial part, then the first challenge is the die design itself is a complicated one. You have to design a die because the die decides the shape and size of your final part. Now, suppose even if you assume that you designed the die, right? You designed the die. That itself complex, but you designed it. The next complication is, little pay attention, you have to pour the powders into that designed cavity. Okay, now when you pour the powder, if it possesses the complex geometries, the powder particles doesn't possess the flowability property, which means the fluidity property. It won't freely flow and occupy the entire cavity of your die. Unlike in the casting process, the die the cavity in the mold is easily occupied by the molten material. So in this case, the second complex is the powder doesn't flow freely and occupy the entire space. This is the second thing. The third thing is, even if you achieve the second, the third thing is you have to eject the part from the dies. You have to eject the part from the dies. Assume the powders been compacted with high pressure, right? So that means the powders in every direction try to escape, but then it cannot escape because of the die wall. Okay, so the die wall and the powder, in between there is a high force that eventually brings the high friction. So due to the high friction, if you want to eject the parts likely to get damaged rather than coming out with the full quality. So that's the third complexity. The next complexity, that's really technical. You know what? When you apply the force, the density distribution should be uniform. You know what I'm talking about? Suppose you take, for example, the cylindrical part itself. You applied it and you measure the density of it, whose density divided by the ideal density of the particular material. You found out it is 90%. Now you take in this particular cylindrical material, at any particular point it should possess 90%. It won't be. The density distribution will be ununiform. If it is ununiform distribution, remember, when it's subject to the mechanical property, the stress distribution is also ununiform. If the stress distribution is ununiform, that means it concentrates on one particular point, that leads to a premature failure. So these many complexities are there. All those are all really engineering problem, and how you are addressing that, or how you are working on it. This is really important in ppm. To prove that, I had given some examples here. You see this one, the density distribution. The black one is like high density, and as you move through, the density is decreases. This figure and this figure, the difference is I'm applying force only in the top direction. Like you take the compaction one, only one direction I'm applying. So this one is I'm applying two directions. So little uniformity you can achieve in the density distribution. You see this? So yes, so this is a proof that how the density distribution is there inside your part. And here I'm giving you a proof, the part ejection complications. The part ejection complications. As you see this is the powder which has been compacted, and you are ejecting it. While ejecting, due to the die and the powder friction, it exhibits some crack here. So something like this, it's even like breaking at this particular point. So these are all the complications involves as you move towards a complex geometry if you want to produce. So this is the second thing. And the last one is, in a general sense, remember, any material you develop, I already told you one thing. You know what? There is two things is really important. Number one is manufacturability. You should be able to produce the part through an existing manufacturing process. So that's exactly here. If you make a part, the workability characteristics should be revealed. It's very, very important in any material development. How we are able to produce. Will you be able to produce it or not? So that's called workability study. A strain hardening I just added. There are plenty I can add, but one of it I added. Suppose if you do your mechanical process through cold forming, or even for that matter hot forming, it undergoes strain hardening. So how the strain hardening is influencing the material, which we can reveal it. Apart from workability and strain hardening, in each process, remember, in each process, there are several operating parameters involved, and it influences the chosen study, say workability study and strain hardening study. You can establish that characteristics as well. And finally, these parameters, like when large amount of parameters involved in this particular study, it is also important to model the process parameter. You know why? Every time you don't want to invest your energy, your material, your time and the cost to make the part, and then you establish the uh, characteristics or material properties. Once you model, I mean to say that mathematical model will predict for you instead of doing a experimental work. So this is also is really important place where you can explore a lot of research work. All right, friends, we almost come to a conclusion. So PPM is all about this. The last one is sustainable. Will this research field is survivable or sustainable? Okay, the last thing, but really important thing. This is not only applicable to this PPM, it is also applicable to any research field or any field for that matter. There's one fundamental question you can ask: is this research sustainable in the market? The answer to this is this process meets the sustainability criteria? Right now, you need to know what is the sustainability criteria. Sustainability means what? My friends, I'm not sure in our BE curriculum we are giving importance to this sustainability or not, but in the real time scenario, the sustainability is really captured the entire research market as well as the industry market and so on, especially the 21st century. There was a talk about sustainability like quite some time, maybe two decades or 3 decades, but then it's really come into a picture these days, like in the 21st century. What is sustainability? Any activity, remember, any activity or any technology that you develop or that you bring it up, it should satisfy or it should be scrutinized through three important things. One is economic, other one is social, other one is environmental. Typically or traditionally, any technology will be developed to satisfy the economy, not about social and environmental in a real sense. Maybe they do some kind of thing, but then in reality, we are almost all the time compromising the environment and social things, and we are going towards economic. I don't have to say much of the examples. The example is already there. We are already experiencing, so which itself is enough. Okay, so whether this process or any process for that matter meet sustainability criteria, then it survive in the market. If it doesn't meet, then in a long run it won't survive. It will definitely be obsoleted. Right, so that's what I explained here. It's a pioneering concept and it captures the 21st century, and it is important to undergo economic, social and environmental process. Remember, truly and ethically, then only it can survive, otherwise it cannot survive. Now, so PPM's viability can be explored. Here it is. So when you go for it, you can really explore that whether PPM can viable through this process or not. Theoretically, I can say here, because already, like I mentioned, it is a net shape processing or near net shape processing, which means what? All the input material is been utilized to produce the part. There is no wastage, so obviously there is no environmental pollutions. Likewise, we can prove, but then in real sense, it is there or not for a particular material or particular part development, you can still study and then you can establish. If there is any other competitive material that does the job, but you go for it instead of going for this particular process. Anyway, this is it. Now, that is the problem existing. The decision making comes in, whether PPM is best or that particular process is best or this particular process, which process is best with respect to these three criteria. So if the decision becomes more and more complex, it's not so easy like two of you or three of you or a panel of members can make a decisions. So there should be some scientific method to analyze and give you a proper solution. That's exactly here MCDM, which is multi-criteria decision making approach. There are plenty techniques are there. if anyone is expert in your in your institute, that you can discuss with them to explore this concept. Usually this is an industrial engineering or operations management concept. You can bring that concept into our technical studies to see whether it is sustainable or not. Now the last one is totally away from whatever discussed so far, how the technology or the research is heading to from the 21st century and in future. Here it is. The technology at its best, almost it appears like we achieve saturation state in many field of engineering. So what I mean to say here is like through technology, whether you believe it or not, in many field we have achieved the saturation state almost in many field. In fact, there is a study, I mean real study. It states that the people die out of obesity is much more than the people die out of famine. So I don't mean to say that the famine is totally out from the earth. It is there, but as compared to that, the because of femininity or because of the war, because of the terrorism, or even for that matter because of that what do you call disease, if you see the death, which is really really less as compared to obesity. So the future, I'm not it's not that my prediction, the prediction is done by Stephen Hawking's, you must be knowing it. He's a familiar physician, now he's no more. And then Yuval Noah is a famous history author. He is, it goes towards biotechnology and infotechnology. The biotechnology is all about genetic engineering, which may take over the human brain, and infotechnology is all about artificial intelligence, machine learning, which is the advancement of infotech that may lead to take over the human work. I'm not going to afraid here, scare you, but I'll tell you a simple thing, and then I'll close this presentation. See, the human possesses two important quality for this matter. You know what? One is physical quality, physic, and the second is cognitive ability, meaning depending on the situations or depending on the experiences, the mind takes that and then it process that, and in future in a given situation how to react or how to respond to that, that's called cognitive ability. The first one is physical ability. Okay, now if you look at the past, how the technology is meeting or is like sidelining the humans, physical ability, the automation can take over. This automation is not a new concept. It's there for quite some time, like right from, like I said, middle of the Second World War or before that, from that day onwards. Even that day, people are afraid, like, what if the automation comes and people would be going without any job or so. But then on contrary, what happened? On the one hand, automation is developed, so the job opportunity is also developed. That's a different story. Now, the next approach is the cognitive ability. Like the human has only got that ability to think and react to a given situation. Now that is being taken over by this info technology, the database, so-called artificial intelligence. For that matter, artificial intelligence is doing much better than even human, and that's the real threat in future. Whether we all of us get like, the technology or the job opportunity is a human based or totally technology based. There is a solution which is like in a general sense, unless and otherwise like we are uniquely talented or skillful in any field, it would be really difficult in future to survive. This is the predictions and I have inclination to that. Well, I stop my presentation here and I'll take up any questions that if you have, and I have referred, these are the references. I admit that it's a 1 hour time, and as much as I wanted to give you some little breadth and depth about this topic, and future if time permits, I'll go a little deeper into that PM techniques, like what are the works we have really done and how the results are revealed and how we can interpret the results from there, what is the usual output that we are getting it, all those things we can discuss. Thank you so much for your attention, and I'm sorry whether if it is bored, but if you have any questions, I'll try to answer as best as possible. Thank you.
Thank you, sir. Thank you so much. You are not bored actually. You have started from the basics of engineering book, and you have landed up with even the challenges, and even the fresh researcher can have the better understanding in which wherein they can have the how to face the challenges. You told the density and the complex geometry as the problems that we generally wants to rectify. Thank you so much. And also, you have enlightened about bioinfo technology. Really, we never actually heard about it in such a fashion. You have even incorporated that with your presentation. And actually, we got two questions, sir. One
Please.
is, uh, is impregnation and infiltration technique come under interstitial or substitutional, sir?
Oh, okay, okay, okay. My friends, the substitutional solid solution, interstitial solid solutions to be understood in a different context actually. It comes under solid solution. You can remember that solid solution. Solution means solvent and solute put together. Whether it is homogeneously stable, even the solid state, we call it as solid solutions. Now, if the solute occupies or substitutes the solvent atom in preparing the alloy, then we call it as substitutional solid solution. Interstitial is like it doesn't have that much ability to substitute the parent atom. What happens, like in between the parent atom, it just takes a small location, like it just takes place there. That's called interstitial. Now, keeping that as our basic, coming here, impregnation, interstitial, it all depends on what we inject into it. If the atoms possess that much atomic, I mean the size, then it can substitute, otherwise it can place there as interstitial. Hello, is that
Thank
okay?
you. Yes, sir. Thank you, sir. Hope you have answered to that. And comparing to 3D printing powder metallurgy and versus normal powder metallurgy technique, which one is superior? Your opinion, please.
Okay, 3D printing. Okay, see, usually it's a metal additive process. The metal additive process, usually the polymer materials or the parent material or the source material to produce the part. And there are some exception is there. If I'm right, like selective laser sintering or some other 3D, for that matter, even 3D printing also been utilized for metal materials to produce part. In terms of strength aspect, the 3DP is inferior than the conventional PM process, but it depends on what applications that we are going for. That decides which process that we can take it. Usually for the modeling, the rapid prototyping itself is like rapidly making the part prototyping, the producing a model of the actual part. So which means that for that matter 3DP is okay, but for the actual applications it may not be suitable. That again, end of the day, it depends on the end applications.
Thank you, sir. Hope you
Thank
have
you.
answered for them.
Thank you.
And we got all our the positive feedbacks as of now, sir. So thank you so
Thank
much
you.
for that. And you really made us densified by your PPM presentation.
Thank
Surely,
you.
surely we will take it up, sir. Most of the people, those who are in the research areas, surely they got the insight about all your challenges given to us and how the 21st century will look out. Thank you, sir. Thank you so much. We'll
Yeah,
meet you on
fine.
another session. Thank you, sir.
Thank you. God bless you. Thank
Thank
you
you,
so
sir.
much for all of you. Bye bye.
Thank you, sir.